welcome back to Tollefson Physics. So we've looked at an elevator acceleration, but what about when the acceleration's in the horizontal direction, such as with the fan cars that some of us are building? And so we're going to look at how to apply Newton's second law in that horizontal direction. So what we're going to start with is we're going to look at a fan car example. That fan car is 200 grams. The force of the fan is known to be 0.44 newtons, and the force of friction due to, say, the axles on the car is known to be 0.04 newtons. So first we're going to determine the acceleration of the car, but then we're going to say, oh, the car runs for 5 seconds, and then the engine cuts out. And so how fast is it going to be traveling after 5 seconds, and how far did it actually go? Right, so now we're going to mix force and Newton's second law with the acceleration and velocity time graphs that we did before. So I'm going to start by drawing a force diagram because we have a lot of force information. Now I could put the force due to gravity and the normal force on my force diagram, and I actually know what those numbers are because 200 grams, which is 0.2 kilograms, times 10 newtons per kilogram for the gravitational field will give me a gravitational force of 2 newtons. And since there's no acceleration in the vertical direction, I know the normal force is 2 newtons. All right, but let's actually put the direction of acceleration so we can calculate something about this. So the force of the fan is 0.44 newtons, and the force of friction is 0.04 newtons. So as we did before, we're going to calculate the acceleration using these forces. And so acceleration is the net force divided by the mass. So in this particular case, the net force is going to be the force in the direction of my acceleration minus the force in the other direction. And the mass of this is 0.2 kilograms. So remember, even though we're making measurements in grams because that's the size of the car we have to use kilograms when we're using anything dealing with newtons. All right, so when we do this calculation, we end up with, well, let's just write A equals, we get 0.4 newtons divided by 0.2 kilograms, and so that actually gives me 2 meters per second squared. Remember, newton divided by kilograms is the same as meters per second squared. Well, what about, so now let's do the part of the problem that involves a velocity time graph, right? So I just figured out the slope. The slope is 2 meters per second squared. I know the time in this particular case, 5 seconds. So what can I solve from that? Well, let's start with equation of the line, the slope, right? So slope is acceleration. What is it? Rise, which is change in velocity, over run, change in time. And so we actually want to know, we know the acceleration, we know the time, so let's cross multiply these, and you end up getting the velocity equals the acceleration times the time. So now I can go ahead and say V equals 2 meters per second squared times 5 seconds. So that final velocity is going to be 10 meters per second after 5 seconds. Now once I know the height of that, I can actually figure out how far it goes if it's on for just 5 seconds. And so I'm going to use my area equation. So area is the displacement. Since it's a triangle, it's going to be 1/2 times whatever the base is, that's the time, and whatever the height is, it's the velocity. Well, I know both of those now, so this is pretty easy to solve at this point. So 5 seconds, and then my height is 10 meters per second. So you can do this however you want. 5 times 10 is 50 divided by 2. So the car, in this case, goes 25 meters. All right, so now let's go to what happens if the fan turns off. All right, so if the fan turns off, our force diagram from here is going to change. Basically, force of the fan's gone bye-bye, right? So the force of the fan goes bye-bye. So my new force diagram, so force due to gravity is still 2 newtons, the normal force is still 2 newtons, and the force of friction is still, 0.04 newtons. So what it's asking is, what is the acceleration now, and how much further is it actually going to travel? So the acceleration isn't too bad. We're going to use Newton's second law. We just have a new net force now. And so our new net force is 0.04. and our mass is still 0.2 kilograms. So this acceleration now becomes 0.2 meters per second squared. All right, so 0.2. So it's actually 10 times less than it was before, because the net force is 10 times less. So it works out that way. So now let's go ahead and draw a velocity time graph, just to remind us of what we're trying to do. This time we don't know the time. We don't know the area. We know the slope. And actually, I drew that graph backwards. It's okay, because it's the same triangle. Let's not draw that graph as just a mistake. We can fix that mistake. It's slowing down. Slowing down. So I used to writing speeding up. I wrote a speeding up one. So you got to be careful of what it says. So the slope of the line doesn't change. Now, is the slope technically negative? Yeah, it's technically negative. But I know the height, though. The height came from the other part of the question, and I rewrote it up there as 10 meters per second. So now I can actually figure out how far it went. Well, or can I? I don't actually know the time, so I'm going to have to figure out the time first. So once again, my slope equation. Slope is acceleration, and change in velocity, change in time. Technically, it's a negative acceleration, and delta V is technically negative. But if we look at the magnitudes, the math actually works just fine. And so in this case, I want to solve for t. So if I cross multiply, well, basically switch the a and a t, you can do that. And then you can substitute, okay, the change is 10 meters per second, and the acceleration is 1/5. And so since that's 1/5, it's like multiplying this by 5. So it actually ends up being 50 seconds, right? The friction's super low on this, and so it's going to keep going. It was going at a pretty good clip, so 10 meters per second. It's going to go a pretty good distance. What is the distance? Well, that's the last question, right? So x equals, so it's a triangle again, 1/2 the base times the height, and so 1/2 times my new time, 50 seconds, and my height, 10 meters per second. So you can do this however you want. So I guess we could do 50 times 10 is 500. Divide that by 2. So this goes another 250 meters. It's quite a distance. Quite a distance. And so if you're able to achieve these kinds, so a realistic small scale fan car is not going to achieve this. If you had something that was really aerodynamic with a high force being applied for a large amount of time, 5 seconds is a large enough amount of time. You get up to a speed of 10 meters per second, and then it takes a long time for it to slow down. And kind of compare these distances, right? The acceleration is 10 times different. The distance ended up being 10 times different, right? So 25 meters when the engine was on, or the fan was on, 250 meters when the fan was off. Okay, now it's your turn. So your turn, I want you to look at a 5 kilogram block, and we're just going to push it somehow, say a hand, with 3 newtons of force for 10 seconds. The friction force on that block is going to be 2 newtons. So after 10 seconds, the block, we're going to let go of it and let it stop. So we're going to kind of put this all together. So during the push, what's the acceleration, what's the final speed, and how far did it go? And then during the glide, after you stop pushing it, well, what's the acceleration and how much farther is it going to go? All right, so pause the video now and give that a try. All right, so first step in solving this problem is, well, let's look at a force diagram, right? So we can get the net force. It's a 5 kilogram block, so I guess I know Fg is 50 newtons, and I know the normal force is 50 newtons because it's not accelerating in that direction. I am saying the forward force is 3 newtons. So the forward force, I'll just say force. And then the frictional force actually is pretty large in this case, but it is a block, so it's not that surprising. And so it's 2 newtons. So we can then go ahead and calculate acceleration is F net over mass. And so the net force is going to be 3 minus 2. And so that's just 1 newton. And then the mass, so what's the mass? It's 5 kilograms. So 5 kilograms. So this acceleration is a bit smaller than the ones we were dealing with before. It's 0.2 meters per second squared. All right, so now if we push that for 10 seconds, how fast is it going to be going? How far is it going to be going? All right, so actually I'm going to put my velocity time graph over here, I think. So velocity time graph, it's going to speed up. It's, we don't know, actually we do know the time, it's 10 seconds. And we know the slope is 0.2 meters per second squared. Not very well written. So since I know what the slope is, let's do slope again. So slope is acceleration is change in velocity divided by change in time. But I want to know the velocity. So if we multiply both sides by t, velocity equals acceleration times time. And so in this case, the acceleration is only 1/5, and the time is 10 seconds. And so that final velocity is going to be 2 meters per second. All right, cool. Wants to know distance as well, so I guess we should do that. So the distance is going to be this area here. So the distance is going to be 1/2 the base times the height. So the base is 10 seconds. The height is 2 meters per second. So 2 divided by 2 is 1. So the distance ends up being 10 meters. 10 seconds is kind of a long time, so it's gonna get somewhere. All right, so then how about part 2 of the problem? So what I'm going to do is I'm just going to cross off the force that goes bye-bye, right? So what's the net force now? The net force is just the 2 newtons going in that direction. So now if we solve for what the new acceleration is, the net force is 2 going that way, and as long as you realize it's going that way versus that way, I'm not going to write the negative sign. I could. But this is leftward, this was rightward according to the direction I drew stuff. And so then 5 kilograms, so this is going to be 0.4 meters per second squared, 2/5. All right, so then we want to know how much further it's going to go. So let's go new velocity time graph. We'll just squeeze it in over here, I guess. Velocity time. We know, where did I put it? Right there, the velocity is 2 meters per second, so we can start there, 2 meters per second, and then it's going to stop. We know the slope, right there, is 0.4. So let's go ahead and use the slope to figure things out. So slope is acceleration, rise over run. This time I want to know time, so I can actually switch the position of A and T by a way of cross multiplying. So that ends up being the velocity divided by the acceleration. So what's my change in velocity in this case? It's 2 meters per second. What's my acceleration? It's 0.4 meters per second, which is the same as 2/5. And so 2/5, it's like multiplying 2 times 5 and then dividing by 2. So the time actually ends up being 5 seconds, which kind of makes sense, right? My acceleration is twice as big as it was before, and so now the time is half. All right, once I know the time, I can figure out how much further does it slide. So because this net force is greater than before, we expect it to slide less, right? So let's see if that's true. So I'll just rewrite what I have here. 1/2 base times height. So 1/2 times the base times the height. All right. So once again, I do have that 2 meters per second shows up in both parts because that's it sped up to it and then it slows down from it. So 2 divided by 2 is 1, and so that final distance, in fact, is half the distance that it slid before. So it slides another 5 meters. So the total distance that it slides is 15 meters if we add those up. All right. So as the more and more that you work on these kind of problems, so when you see something about forces, force diagrams, great place to start, and then see if Newton's second law, F net equals ma, or the way I wrote it here, A equals F net over mass. Can that help me solve something that I don't know? And then we can tie it to velocity time graphs, which allow us to solve everything about acceleration. So the more you practice, the better you're going to get. Good luck.